Okay, we've been talking about temperatures, we've been talking about the sun's energy, we've been talking about winds and pressure. So, what's left? Well, you might want to know if there's clouds in the sky or if it's going to rain or snow on you. And that's the next real variable we're going to look at: humidity, saturation, and stability, all coming out of humidity. So, let's see if we can find some good stuff here about that. So, we got to learn a little bit first about the water cycle in the atmosphere. There are things called atmospheric rivers. They happen sometimes in the wintertime, and you see them across the Pacific. You can also sometimes pick them up in the Atlantic, coming out of the Caribbean and then up into the U.S. But here is one, for example, that's coming into a storm off the west coast of the United States. Look how far back. It goes all the way back, almost into the Indian Ocean. Very tropical Pacific air, very moist air, and it's responsible for a lot of the global moisture that comes into the Pacific states. And you can see here where they hit the mountains and get extreme rainfalls and extreme snowfalls up there. They haven't had a lot of these lately. That's why there's a drought out there. So the total amount of water in the atmosphere is really relatively small. Most of it is confined to the troposphere. And if you removed it all, guess what? You'd only get about an inch over the whole globe. That's not really that much. But water is continually entering the atmosphere through evaporation and the whole global water cycle. So what is that? Well, oceans, lakes, rivers all evaporate moisture. That moisture goes up into the atmosphere as water vapor. Some of it condenses in clouds over the ocean, comes right back to the ocean. Oh, some of it goes over land. Maybe it hits a mountain range and comes up there, falls down the slope. Notice the runoff here. The more the slope, the faster the rain's going to come down. If you're in West Virginia, I worked there for a number of years, and I can tell you for a fact the people that live in the valleys, in the hollers, as I've been told, have a lot more flooding. My in-laws grew up in a creek bed, literally, and literally had flooding frequently near their house. Why? Because the precipitation runs very quickly down the mountain slides into that water, causes it to rise very quickly. Oh yeah, land. Guess what? If you're in a big city, you're not going to get a lot of runoff, are you? Because of all the cement paving that's done there, and the asphalt, and also the buildings. Now, if you're out over vegetation and fields and all that, it's going to absorb a little bit flatter. It's going to absorb more into the ground, but it's also going to release some, especially during the afternoon. Evapotranspiration is very high. So you actually get more moisture in the atmosphere during the late afternoon from plants. So these are the different things that goes through the process. There's evaporation, condensation, transpiration, and evapotranspiration, which is just transpiration and evaporation. Oh yeah, there's also sublimation and deposition and precipitation. All of that are part of the atmospheric water cycle. Well, how do we describe water in the atmosphere? Well, humidity is basically a term. There are various ways of measuring humidity. We know that a hot, humid day in the summertime is a whole lot more uncomfortable than a dry winter day. So humidity must be a factor in how comfortable we are as well. So look at these various terms for describing water in the air. Vapor pressure. Water vapor is a vapor. It is going to have a pressure. Mixing ratio, specific humidity, absolute humidity, relative humidity, dew point, precipitable water. Needless to say, we look at a lot of different variables when we're talking about moisture. So basically, vapor pressure is just the amount of pressure of water vapor in the atmosphere. You don't find it much more than 4%, and that's usually in the lowest 1 kilometer. Mixing ratio, just another way of looking at moisture. It's taking the water vapor mass of the remaining dry air, and that's expressed as mixing ratio. So you pull out the water vapor from a little parcel of air, and you have the rest as dry air, and then you have the water vapor, and that's a percentage or mixing ratio. Specific humidity keeps that water vapor in, so you get the total mass of the air and you have the water vapor divided by that. Slightly different than mixing ratio, not a lot. Absolute humidity is the mass of water vapor per unit volume of humid air, or grams. Saturated air. Say you have a cloud. Looks pretty saturated to me. What is that? Air, it's its maximum humidity. You have fog forming. That is the most water vapor that air can hold. So all these just terms we just used, vapor pressure, saturation vapor pressure, saturation mixing ratio, all of that is just when the water vapor has reached a point where part of it is going into liquid and part of it's coming back to water vapor, and it's steady state. Literally, there's so much going into the liquid side and so much going into the water vapor side. So that is literally a steady state. Can't go push any more water in, vapor in, or change something else, you're immediately going to have all water. Go the other way, you're immediately going to have all water vapor. Interestingly, they're different over ice. Why would that be? Ice is a solid. So the saturated air over a solid surface, and solids, they don't have as much kinetic energy as a liquid does. So the actual saturation vapor pressure is going to be a little bit lower over ice than it is on normal air. So in other words, if you're way up in a cloud, cirrus cloud or whatever, your saturation mixing ratio is a little lower, saturation vapor pressure, than if you had down where the bottom of the cloud where it was all water. Relative humidity is a term you're all used to hearing. It's vapor pressure divided by the saturation vapor pressure times 100%, or mixing ratio. It's basically how much more water can you hold. In other words, if your relative humidity is 70%, you reach 70% capacity of that air parcel. If your relative humidity is 100%, you're saturated. That's all relative humidity is telling you. Notice during the daytime, temperature kind of dictates that. The colder the temperature, saturation vapor pressures are lower, so that the colder the temperature, the air can't hold as much moisture in it. The relative humidity is going to go up. That's why maximum relative humidities and why fog tends to form during the early morning hours. Now, during the day, as the temperature is rising, it can hold more moisture. Guess what? The relative humidity comes down. However, there is a little peak of relative humidity early in the evening where evapotranspiration kind of comes into play. Yes, this is dropping some, but there's also a lot of evapotranspiration going in, raising the amount of moisture in the air. Dew point, if you cooled the air to that temperature, didn't change anything, it would become saturated. So when we look at a plotted weather map, we plot dew point. The higher the dew points are, the more moisture is in that air. And if you look at the difference between the dew point and the actual air temperature, you can tell what the relative humidity is. If the two are exactly the same, you know the relative humidity at that location is 100%. Dew points are pretty much the same as a frost point. Notice in the winter, dew points, most of areas are in the less than 20 degrees typically in January, especially over Ohio and stuff. A little bit more in my area, 20 to 30. Down towards Florida, gets a little bit warmer. Notice the summertime. Dew points are up into the 60s, even greater than 70 in a lot of areas in the southeastern U.S. An interesting tidbit. There's a lot of winter wheat out in Oklahoma. In the springtime, evapotranspiration is so high from that winter wheat that dew points average 10 to 15 degrees more there than they do later in the summer once they've cut that wheat. They literally have looked at that. So plants provide a lot of moisture. That's why the cornfields in Iowa sometimes in the summertime can help raise dew points 4 or 5 degrees more than they would have been without all that cornfields. So what happens as the air becomes saturated? Well, it's got to do something. You can't hold many more water vapor, so it basically is forming cloud droplets, deposits. It produces clouds. So how is air cooled? Well, we know it's cooled when it rises, because air is constantly cooling as it goes up. So that is one way that the air can reach saturation. Or you can add water vapor into the air from the source to reach saturation. Now we're going to talk about another part of atmosphere: stable versus unstable air. All right, take an air parcel. If that air parcel is colder than the surrounding air, it's going to be denser than that surrounding air. Dense particles sink. They want to go back to where they're become the same temperature as the surrounding air. So if the air temperature is colder, the air parcel is going to want to sink. Now, if the surrounding air, we're going to call the surrounding air environmental air, if that air is colder than the actual air parcel is warmer than that air parcel is going to accelerate upward until it cools to a point where it equals the air temperature of the environmental air. So stability can either inhibit cloud development or it can accelerate it. And it all depends on what the temperature of the air parcel is to the surrounding air. We know air parcels cool at 9.8 degrees on dry air. So if you had the temperature in the environmental air cooling at 8 degrees, if you raise an air parcel 1,000 meters up, you know the air parcel is going to be 1.8 degrees colder than that normal air around it. It's going to want to sink back down. It's going to be stable. But now, let's bring moisture into this equation. Moisture means the air parcel is going to be reaching condensation. And we know that condensation is a warming process. So that means that parcel, instead of cooling at 9.8, is going to cool at, say, 6 degrees, a little bit over maybe. So now if you cool the environmental air at 8 degrees, you go up 1,000 meters, push that parcel up by a mountain or by a cold front, all of a sudden that air parcel is over 2 degrees warmer because it's saturated than the surrounding air. What's it going to want to do? It's going to tend to want to accelerate upward. That's unstable air. That acceleration upward leads to big clouds. Many times leads to cumulonimbus clouds. So here we talk about the two: absolute instability. Almost never see it with air cooling faster than 9.8. You might see it right in the lowest foot towards the ground sometimes. It's actually what causes illusions along the ground. Conditional instability is a little different. And what can cause air to rise? Sun's heating, we know, does that. Mountain ranges, fronts lifted. Mountains. Even with the mountains, there can be a rain shadow. For example, out west, we have a lot of west winds hitting the Rocky Mountains or the Cascades. What happens is you get lots of rain dumped right before or along the mountain range on the west side of it. Precipitation totals go much further, much lower. Surface winds converging, like down in Florida, pushes the air up, forming the thunderstorms. So with that, I wanted to just take you just to look at a little bit of moisture. This is the moisture today at mid-levels, about 15,000 feet up. So, waiting on my friends here at Nestus. Hopefully they'll come up here shortly. And here we go. What you see here is dry air circulating around this area. That's actually an upper level low. Mixes down some stratospheric air into it, and it usually has dry air around it. Now, here in the middle, why do you think there's all these clouds and probably showers? Well, what's happening is that air is very cold, at the upper levels. It got warm at the bottom today, and that causes instability. And we just saw if you have instability, you can get rain. We can look at here along the East Coast, a batch of moisture coming up here out of the Caribbean, all the way up along the East Coast with lots of moisture. Pacific bringing moisture into the Midwest as well, and coming back from Gulf of Mexico as well. So there's something to look at on this kind of a chart. This is a Stuvie diagram. You're getting some of those in your things. I just wanted to look at Charleston, South Carolina. All right, the temperature change here is right here. And it's probably about maybe 7 degrees because it's fairly moist. Here is a very weak green dashed line right there. That is the moist adiabatic lapse rate. That line, if you had an air parcel, would be what the temperature would be. So what we look at doing is taking an air parcel here and rising it along that line. If you did that, it would always be slightly warmer till you reached right here. And then it would actually be the same or cooler. So that's the area that's unstable. Not really a lot of instability here in this island. And finally, I wanted to show you the precipitable water over the United States. Really high, over 2 inches along the Gulf Stream and into Mexico, and here, Gulf of Mexico. And highest precipitable waters are always going to be down towards the equator. And there is some good moisture here off the west coast of the United States as well, coming up out of that. But notice how dry it is out in the west, U.S. here. Very, very dry. You have east winds going down the mountain ranges there right now. So just something to think about, all this moisture stuff. So if you have any questions, please don't hesitate to ask.